Good evening, teacher. Here is the group 2, which is working on study case of asynchronous machine, talking about FOC control. First of all, let me elaborate more, talking briefly about our content. First, we're gonna talking about the introduction. Second, our application. Third, MATLAB simulation. Fourth, result and interpretation. And fifth, conclusion. So in introduction, I want to introduce you briefly about asynchronous motor. An induction motor or asynchronous motor is an AC electric motor in which the electric current in the rotor that produces torque is obtained by electromagnetic induction from the magnetic field of stator winding. An induction motor, therefore, needs no electrical connections to the rotor. And what is FOC? FOC, from the full name of field-oriented control or vector control, is a control technique used to obtain good control capability over the full torque and speed range for various motor types, including inductance machines, permanent magnet, synchronous machine, PMSMS, and brushless DC BLDC motors. In the FOC approach, there are two current loops, one for the Q torque and another for the D torque. The Q torque loop is driven with the user's desired torque from the servo controller, and the D loop is driven with an input command of 0 so as to minimize the unwanted direct torque command. FOC provides good control capability over the full torque and speed ranges. The FOC implementation required transformation of stator currents from the stationary reference frame to the rotor flux reference frame, also known as the Q reference frame. Second point, our application will be talking about FOC's application. FOC can be used across AC induction motors and brushless BLDC motors to improve the control and accuracy of motors for a wide range of applications, from pumps and fans to conveyors, particularly in industrial automation where long-term reliability is essential.
Good evening, teacher. My name is KJ Pisat from the FOC group, and this is this is our system that we build FOC, and as you can see here, we have field-oriented control here. That this is the brains of the system where it is calculate everything. And we have here that convert from radian to RPM, and then we connect the system here to the reverse part where their function is to convert three-phase AC to DC, and we have space vector PWM that control the output voltage of a three-phase inverter by switching the inverter switch rapidly, and it has 6 sector here. And then we connect it to the three-phase inverter and connect it to other motor, and phase and line voltage here is to control mechanism to adjust the error calculation. And in the bottom we have forward part and forward clock that their duty is very similar, but because their function is to convert three-phase AC signal to DC signal. And then we can see the graph by connect it to the scope. So for the next part, we're gonna be talking about the result and interpretation. So when we run our simulink, we get three graph results that we wanna look at. The first of all is the three-phase current, phase A, phase B, and phase C. So as we can see that for every 1 second apart, we set our speed to change, and we can clearly see the current fluctuate. Sorry, current fluctuate depending on the changes in the speed. As the first fluctuation is a bit big, as it has more torque to start the motor, and we can clearly see it in all the three phases. Um, but otherwise the phases are smooth, indicating a smooth control over the motor. Um, so for our torque graph, we can see that our torque is that the first it start from 0 and it went up to um about 900 newton meter almost instantly, indicating there's no lag in the torque. It um, respond to the changes in current fast and efficiently, and we have the torque increases and decreases depending on the speed, whether the speed increase or decrease, and again it in a period of 1 second that we put on it. So this is the torque graph, and the next one is gonna be the speed graph. First of all, we have a reference speed. So the yellow one is a reference speed, and we want to know whether the motor speed can can flow through can be controlled efficiently with the reference speed. And um, as we can see that the motor speed came from 0 and meet the um, reference speed at around 500 rpm, but it overshoots a little bit, but it manages to um, level with the reference speed, and overall it's only a bit undershoot or overshoot along the speed changes. um, it is a um, it is a good efficiency that it only undershoot or overshoot a little bit. Otherwise it is identical to the reference speed, our reference speed. So here is the overall look on the three graph. We can see that as our speed changes from 0 to 500 rpm, our torque increases, and so is our current change. So, and right here we can see that it is then take another increase to around um 900 rpm. Again, our torque and uh current also fluctuate. Right here the rpm decrease as our torque also decreases, and it is then increase again and also decrease again. So we can see the corresponding um it is the three graph corresponding to one another depending on the change in current, which change the speed and also the torque. So this is all for my result and interpretation.